All right.
Nitrogen oxides, or NOx, causes huge environmental damage. The coal-fired power plants in China emit more than 10 million tons of NOx every year, resulting in acid rain, soil erosion, and deforestation. The situation is so alarming that the State Council mandates 30% less NOx emission by 2015. Unfortunately, even with the government subsidies, the existing technologies are way too expensive for the companies to adopt on a meaningful scale. I have developed a microbial-based process that takes the NOx from the waste stream and transforms them into high-value chemicals, which can then be used to synthesize everything from clothing to feedstocks, etc. This process is eco-friendly. More importantly, it allows the coal-fired power plants to recoup their NOx treatment cost from selling the chemicals. This offers huge incentive for the coal-fired power plants to adopt our technology and to improve the air quality. China has an annual market for NOx treatment of over $3 billion per year, and 6.1% annual growth rate projects the market size to $5 billion by 2020. With our groundbreaking technology, NOx treatment is not only an environmental solution, but also a financial one. Thank you.
Thank you. Moving right along, our second presenter is Karthik Murali, and he is from the Biomimetic Microelectronic Systems, BMES. And I apologize for butchering your name.
Good morning. We have developed the Acoustic Roadrunner, which is a portable, rapid, non-invasive device for on-site detection of changes in intracranial pressure, which is a direct symptom of traumatic brain injury. Annually, around 1 million people are diagnosed with traumatic brain injury, or TBI. 50,000 of them die because of this injury. This is also becoming a significant problem in the military and the NFL. Now, for TBI, speed is essential for diagnosis. Studies have shown that the faster the diagnosis, the higher the chances of survival. However, as of now, there is no technology that can detect the severity of TBI at the site of injury. This has led to patients with mild to moderate cases of TBI to be wrongly triaged into trauma centers which are not capable of handling these cases. This is where we come in. Our technology can detect the severity of TBI at the site of injury, allowing for accurate triaging, saving precious minutes, and improving chances of survival. When field paramedics place our disposable patches on the patient's head, the piezoelectric transducers generate and record acoustic waves that travel across the skull. With this information, they can convert it into diagnostic images on a display screen, which indicates the severity of TBI. Patients can then be accurately triaged, increasing their chances of survival. Thank you very much.
No clapping, no clapping. All right, our third presenter. Oh, time, sorry. How's the weather? It's pretty cold out there. It was 75 degrees on Monday. I knew you were good at this. Was this anyone's first annual meeting? Any newbies? Welcome. You'll be coming for a long time, especially if your center is newly funded. Any new SLC members? No? Yes? Great. We have our next contestant, Justin Jasper, from Reinventing the Nation's Urban Water Infrastructure, Renew It. Oh, wait. Oh, yes. Where's Justin? Oh, okay. You confused me for a second.
But that's not my slide. You're gonna switch and then I start? Okay.
There you go.
Conventional wastewater treatment plants, while effective at removing organic matter and pathogens, were not designed to treat the thousands of trace organic chemicals we use every day. This class of pollutants, which includes biologically active compounds such as pharmaceuticals and personal care products, may negatively impact aquatic ecosystems in receiving waters, for example, by inducing the feminization of male fish. In addition, these compounds may pose challenges to water reuse projects, which are becoming increasingly important in water-poor regions around the world. To address this issue, we have developed the Purified Enhanced Oxidation Process, or POP for short. POP consists of a shallow open water cell where trace organic chemicals are removed via two mechanisms: a reaction with natural sunlight and biotransformation in the layer of biofilm termed periphyton that rapidly inhabits the bottom of the cell. POP, in contrast to existing technologies, is inexpensive to install and requires minimum maintenance. Since treatment is provided by natural means, no energy input is required and the process is carbon neutral. The only byproduct of POP treatment is a nutrient-rich material that can be used as fertilizer. Thus, investment in POP will result in improved quality for our nation's precious water resources at a fraction of the cost of alternative technologies. Thank you.
No clapping. I know it's really hard. Air clap. I've been told that you can now clap. So our next contestant is Daniel Mateo from the Center for Structured Organic Particulate Systems, CSOPS. Don't go too far.
Education and outreach is a key objective of the ERC. It is important then to understand that 99% of engineering schools in the US do not have a pharmaceutical engineering program. Therefore, there is a lack of prepared graduate students with pharmaceutical engineering skills at entry level, requiring industry to spend more time and money to train the new employees. My solution is the Center for Pharmaceutical Engineering Development and Learning. Our goal is to prepare students in the pharmaceutical engineering area. Funded by NSF, the center implemented in 2005 a certificate in pharmaceutical engineering. The students also do research in our lab in which they develop technical and communication skills. Since 2008, more than 450 K-12 students have also been impacted with hands-on visits to our lab. The result of this initiative is that our students are better equipped at entry level, requiring less training time. This is clearly within the objective of the ERC, and it benefits both the community and industry. My name is Daniel Mateo, and we want you to invest to continue and expand our program so we can provide you with qualified talent ready to impact your organization and deliver results. Thank you.
So it's not every day I have a stage, a microphone, and a room full of people looking at me. So I'm going to take advantage of this in our intermediate time. So ask me anything, almost anything. Let's be interactive. Anyone wants to know anything about me or anyone else in this room? Does anyone snowboard? I snowboard. Where do you board at? In Vermont. Pretty nice. Skiers? Ski? Well, y'all have to concentrate, so y'all aren't in the conversation. Just playing. Where do you ski? Tahoe. Oh, fancy. Tahoe. I want to go to Tahoe. Any cyclists? Cyclists? No? No bikes? Do you have a mountain bike or a road bike? Road road bike, Trek, Cannondale, Specialized. Oh, leaving this in the next 3-minute break. But for now, we have our next contestant, Robert Palumbo from the Collaborative Adaptive Sensing of the Atmosphere Center, CASA. I'm going to press it.
Severe weather in the United States causes billions of dollars in damage and affects the lives of millions of people each year. Existing weather sensors provide inadequate coverage, but municipalities cannot afford the cost of additional technology. My research is focused on driving down the cost of a key component of a weather sensor, the signal processor. Now, traditionally, there are two options you can take when choosing a signal processor for your system. You can purchase a standard COTS component, which can cost upwards of $15,000 to $20,000, or you can design your own board, which is cheaper but can take 9 to 12 months to achieve full functionality. As a logical middle ground, my research is focused towards the development of a signal processor utilizing existing hardware platforms in adjacent markets. Many companies in the telecommunications industry offer low-cost signal processing boards that contain the same hardware components as on expensive COTS devices, but perform entirely different functionality. I've developed my own signal processor that performs all of the processing required of a weather radar sensor that can be integrated into one such device. My signal processor achieves a 10 times cost reduction over similar COTS devices, which enables the affordability of small-scale weather radar networks within the United States. Thank you.
I would like to applaud the contestants that went already. No one has even gotten close to being interjected on. Everyone's keeping to their 90 minutes, so that shows good preparation. So kudos to y'all. Excuse me? That's what I said? Ah, well, you know what I mean. 90 seconds. Our next contestant is Kumaraguru Prabhakar from the Center for Ultra-Wide Area Resilient Electric Energy Transmission Networks, Current. And I did that wrong. Hold on. Can we reset? All right, so when I switch, it'll reset? Okay. All right.
This is...
Oh, gosh. All right.
5 months ago in India, a trip power line caused a blackout which affected 700 million people covering 22 out of 28 states. It was the inability to monitor the load centers and control the power drawn from these centers that caused the blackout to cascade. Imagine a summer morning with no aircraft, no trains, no traffic lights, and worst of all, no air conditioning. It was a chaos. Currently, India is taking initiatives to deploy wide area monitoring system. Could something like this happen in America? In 2003, a transmission line overheated, sagged onto a tree, and caused a blackout. And Lawrence Berkeley National Laboratory suggests that the US grid averages 90 to 200 minutes of blackout time per year. NASA released a map of US with transformers vulnerable to solar flares, which can cause probable system collapse. Can we fix these issues? Yes, we can. Frequency disturbance recorders send information from substations to servers. A wide area monitoring system will use this information to show how a blackout will cascade throughout the continent from Arizona to British Columbia. A wide area control system will use these signals to control power system elements like generators, transmission lines, and circuit breakers. We need to improve our current technology to meet this event before this future threat becomes a present threat. Thank you.
Our next contestant is Robert Lovelet from Quantum Energy and Sustainable Solar Technologies.
We're already starting to see the effects of global warming. Rising seas, shrinking glaciers, more frequent, more intense heat waves and other extreme weather. Fossil fuel vehicles just perpetuate this effect. But right now, electric vehicles are only a small improvement. If you're charging from the grid, you're just pushing most of your emissions back to the power plant anyway. We have a solution: community-based solar charging stations. Charging off-grid from solar makes electric vehicles truly emission-free, but the investment is too high for the average individual. We expect our clients to mostly be moderate-sized businesses, like universities or hospitals, with a lot of commuters who will charge their vehicles during the workday. We expect these clients to use any excess power produced either to offset electricity costs or to fuel their own all-electric fleet. The community-based model has worked in other cases. Think of a propane filling station or even a typical gas station. Other companies have similar plans in place, but they're focusing either on the residential market for individuals or on building standalone stations like at highway rest stops. We have the team in place that we need to put this business into action. The University of Delaware and its partners at Quest are known for world-class solar energy research, and we have several contacts in industry. Thank you.
Our next contestant, and please excuse me for mispronouncing your name in advance, is Iva Evans from the Engineering Research Center for Sensory Motor Neuroengineering.
Have you ever been in a car accident or taken a really bad fall? What if it had left you paralyzed? It can happen to anyone: athletes, actors, even scientists and engineers. Just one accident and you could lose everything. 250,000 Americans have suffered spinal cord injuries, the most common resulting in hand and arm paralysis. And the cost of their care is approaching $4 billion per year. But what can we do? Current treatments are not enough. No combination of physical therapy or electrical stimulation has been able to restore volitional control of a patient's paralyzed limbs. But that could all change. At the CSNE, we're working to engineer neural devices that help people. This one is designed for patients with spinal cord injuries. We call it the NeuroChip Plus. It works like a prosthetic spinal cord, recording the intent to move in a patient's motor cortex, transmitting that signal around the injury, and stimulating healthy motor neurons below the injury to innervate the muscles of the arm and hand. It is small, implantable, and customizable. Now, there's still a lot to do before this device can go to market, but if we are successful, we could drastically change the prognosis for spinal cord injury. Just imagine what it would be like to be able to feed yourself or dress yourself again after having others do it for years. Our device could truly transform lives.
All right, so our next contestant is Amy Chaya from Revolutionizing Metallic Biomaterials.
Bone fractures are an extremely common injury, causing over 10 million hospitalizations each year in the US and driving a $3 billion industry to make internal fixation devices. Among these devices are plates and screws used to stabilize bone fragments during healing. Now, traditionally, these devices are made from permanent metals like titanium, but these cause complications in 40% of patients, including long-term infection, bone weakening, and even bone refracture. To avoid these complications, the devices can be removed, but this requires a second surgery, putting patients at additional risk and increasing the overall treatment cost by $60,000 per removal. Even degradable polymer devices have been tried, but their mechanical limitations make them inadequate for weight-bearing applications. Well, our ERC thinks there should be a better way to have metallic strength without those complications. So we're developing OsteoMag. The OsteoMag fixation system exemplifies our ERC's work to revolutionize metallic biomaterials. Our plates and screws are made from patent-pending degradable alloys, uniquely engineered to provide fracture stability while degrading slowly and safely. This allows our devices to facilitate healing while eliminating the need for a removal surgery. Preliminary animal studies with these devices has already demonstrated healthy fracture healing, new bone formation, and gradual device degradation. And we're extremely confident that our next round of studies will further demonstrate the ability for these materials to not only facilitate, but enhance fracture healing. Thank you.
So my iPhone's going to help me out for this session. I have a joke. So, Murphy's 10 laws for experimentalists. In a scientific experiment, if something can go wrong, it will do so just before your grant is up for review. If the reading on your detector is correct, then you've forgotten to plug it in. Haha. Like, make it stop. All right. Our next contestant is Joshua Claypool from the Engineering Research Center for Biorenewable Chemicals.
This morning, when you woke up and you checked your smartphones or your laptops for emails and texts, did you ever consider what went into making these devices? Most of us use these and other items that are made with petrochemicals every day. Things such as the shirt you're wearing, the tires on your car, and that seat you're sitting in are made with petrochemicals. But now the crude oil supplies that offered us a plentiful and cheap supply of petrochemicals in the past are now steadily increasing in price and decreasing in availability. To combat this problem, CBERC is developing renewable chemicals by re-engineering organisms by creating novel catalysts. However, not all chemicals can be created in an inexpensive method that achieve the utmost in renewability. So how do we find these new chemicals that can compete on both levels? The answer is BioPET. BioPET is a biorenewables process evaluation tool that models the costs and carbon emissions of chemical engineering operations to provide analysis at an early stage in process development. Most process evaluations come once we've climbed this tree far enough to see whether or not we have a good or bad apple. This is where BioPET differs. BioPET allows these analyses to be conducted while still standing on the ground. Why risk climbing this tree just to find a bad apple when we can improve our chances of finding more fruitful opportunities without the extra risk? Thank you.
Contestant is Levi Stanton from the Mid-Infrared Technologies for Health and the Environment.
Today's methane sensors leave scientists, industry, and government agencies blind to many sources of methane emissions. Meanwhile, methane emissions threaten the climate as a potent greenhouse gas and compromise industrial safety by having leaks. Our new technology developed at MERTH now provides a real-time, high-resolution picture of greenhouse gases, detecting instantaneous hotspots that current sensors are completely blind to. This new visibility will enable researchers to better understand methane, for government agencies to enforce more effective regulations, and for industry to increase safety and reduce losses by targeting leaks in areas such as oil and gas refineries and fracking wells. Our system utilizes a quantum cascade laser combined with a long integrated path to see very small changes in methane concentrations. An innovative use of proprietary calibration techniques, low power design, and a rugged enclosure allows for open gas sensing wherever we use it. In fact,
a sensor
so robust, while I was observing it lasted during an Arctic snowstorm, my beard froze over, but it continued to give measurements. This system will dramatically impact the $500 million a year market for greenhouse gas sensors, but more so, it will make major new insights into methane emissions and how to reverse global warming. Thank you.
Next contestant is Jasmine Sears from the Center for Integrated Access Networks.
Silicon photonics is poised to revolutionize the telecommunications industry. But first, we need a better laser. Currently, 1500 nanometer light, the wavelength preferred by telecommunications, is generated externally and then piped into the device using a series of waveguides. Unfortunately, this method takes up a lot of space. It's also lossy, which leads to higher power consumption. The Cyan ERC is developing a compact, efficient optical solution to data aggregation, and off-the-shelf components just don't cut it. Our group is working to provide our ERC with an integratable telecommunications wavelength laser. We're using erbium, an element that emits at the desired 1500 nanometers. By incorporating this active emitter into a special type of silicon waveguide cavity, we can turn a section of waveguide into a tiny laser. Because this cavity can replace a section of existing waveguide, it cuts volume requirements in half. And because the light is generated internally, there's little opportunity for loss. So where do you come in? Simply proving this method works is worth a journal article at best. But optimizing it to outperform the industry standard would facilitate a huge breakthrough in device miniaturization. With your support, we could realize massive gains in compact, low-power telecommunications technology. So, are you interested?
Our next contestant is Brian Frey, and he's from Smart Lighting Engineering Research Center.
Lockheed Martin built a new daylit facility in California and found that productivity increased by 15%. HMG did a study of second grade to fifth grade classroom students and found that students with more natural lighting did up to 18% better on standardized tests than those without. A study from the University of Milan found that length of stay for bipolar hospital patients decreased by over 3 days when they were kept in rooms with direct sunlight. These examples demonstrate how beneficial natural lighting can be. However, there's no easy way to integrate sunlight into every indoor space. To address these problems, we need to have adaptive lighting systems that can mimic sunlight. This can be achieved through an integration of sources, controls, and sensors, but the sources need to be a mix of several well-defined colors of LEDs. This is where my research comes in. I'm creating photonic crystal optics and organic phosphors to create new colors of LEDs that have fast response times and don't use rare earths, which are in short supply. The result is more versatile lighting sources and an increased ability to generate truly healthy light, so we can put smart lighting in offices to make workers more productive, in schools to help children learn more, and in hospitals to help patients heal faster. Just think of everything that we can do with the right light on our side. Thank you.
Our next contestant is Tia Simpson from Freedom Systems.
Did you know that every time you turn on your laptop or your TV, you're taking advantage of the power electronics circuit within? Power electronics packaging is the physical formation of a power electronics design. Current systems of power packaging need to keep pace with the lightning-fast changes in the electronics world. We can solve this problem through our revolutionary 3D printing technology. Our methods reduce rapid prototyping time from 4 to 6 months to just a few days, introducing a profitable product in a quarter of the time. Our approach also reduces final product weight and waste of materials through 3D printing's ability to print complex hollow objects. Our technology also introduces new capabilities such as printing on non-flat surfaces using uniquely flexible or transparent materials. Remember your laptop I mentioned earlier? Well, with companies such as Dell and Apple continually compacting their products, we can meet their needs through our ability to stack, print up edges, and move components closer together. Most importantly, our significant contribution to bringing the Freedom System smart grid projects to fruition. Our unique method of 3D power electronics packaging is breaking into a $20 billion market. And we are leading the industry. Thank you for your time, and I look forward to having you visit the Freedom System Center to witness our achievements.
So, our next contestant is Shivayogi Hiramath from the Quality of Life Technology Center.
Studies have shown that 75% of 3 million wheelchair users in the US will develop shoulder pain, rotator cuff injuries, and carpal tunnel syndrome due to improper technique and overuse of upper extremities during wheelchair propulsion. The estimated cost of shoulder dysfunction in wheelchair users is about $450 million during their lifetime. To address this need and the reduced number of therapy days during rehabilitation, we are developing a physical activity monitor system which can be used as a clinical tool to coach wheelchair users to perform optimal propulsion to avoid shoulder dysfunction and significantly reduce healthcare costs. Through the use of an accelerometer, a data logger, and a smartphone, we track upper arm movements, distance traveled, and calories burned during activities of daily living. We utilize our expertise in wheelchair propulsion, innovative machine learning algorithms, and coaching to provide users with real-time feedback about their current propulsion pattern and the optimal pattern that they can attain through audio and visual cues. The technology is modular and can be used in other activities such as running and cycling. We have had local and national requests for this technology and hope to empower wheelchair users to lead a healthy and active lifestyle. Thank you.
So we're on to our last contestant, last but not least. We have Kathy Hochboom-Pott from the Center for Extreme Ultraviolet Science and Technology.
Every year, you can find another new smartphone, each one more powerful, more efficient, and somehow smaller than the last. The engineering behind these devices and the progress needed in nanofabrication to keep making these smaller and smaller components has been truly astounding. The problem is we can now make structures smaller than we know how to measure, which means we have no way to understand something like heat dissipation at this nanoscale, or the way material properties might change in small structures. We need to scale our measurement tools down to the structure size we care about. And the ruler works just fine to measure a whole snail, but not a single cell. And for nanostructures, we use nanoscale extreme ultraviolet light in a way that's affordable and small enough to fit into a production line. For example, we excite a set of nanostructures, watch them heat up and cool down, seeing thermal expansion smaller than the diameter of a single atom, thanks to measurements with light on the right scale. By comparing our observations with the existing models, we see that nanoscale heat flow behaves rather differently from what we might expect. And you can't have your phone melt down just because the heat load wasn't properly accounted for. This is the kind of understanding necessary for future technological development, denser hard drives, smaller and more efficient processors, and new technologies not yet invented. Our EUV technique can enable the all-in-one measurement tool we need to understand this nano world. Thank you.